suggestions. Whenever I try to explain the topics that we see in context with daylight, I usually use this beautiful picture. It is the picture of the woman at the window. It's painted by the German painter Caspar David Friedrich. You can visit this picture in the National Gallery in Berlin. It was done in 1822. And I think that a lot of topics that you as well mention can be seen in this picture. What do I mean with this? For instance, if my laser pointer would work, then okay. First, if we have a look at the outside world, that is illustrated in a very detailed way by Caspar David Friedrich. We can see a partly clouded sky. We can see different types of trees and vegetation. We can see the mast of a sailor's ship. So we can get an idea where this scenery is placed. And it's one of the most important questions that we have to ask ourselves. Are we building for the hot and dry? For instance, here, like some vernacular architecture examples here from Eastern Africa, or are we building for the hot and humid, like those very sophisticated and very, very elegant buildings here of the Batak in Indonesia, where the geometry and the design of the building has a major influence on the indoor comfort without using any technical devices? Or are we probably building for the cold, like those igloos of the Inuit in Greenland, with very, very compact forms, but, for instance, that enable temperature differences between the inside and the outside of more than 50 degrees of Celsius, which is a very, very remarkable number. So the scenery and the situation has to be first considered. The next step is on the building envelope that we have to have an eye on. Remember, this was painted in 1822, so we can consider that, for instance, the glass panes and the qualities of the glazings here are completely different as we have it in nowadays. We have a very specific position of this window here, and on the other hand, the woman at the window has the possibility with this very, very simple device to keep herself protected, for instance, from glare, from horizontal impining sunlight, or probably she has the possibility to keep herself protected from people from the outside. I have picked out a very, very special example that you probably know. Do you know this building? It's the Institution Montarab.
Yeah, like merge between Arabic design and modern design.
Exactly. Yeah.
Center of Arabic culture.
Exactly.
Somewhere.
Did anybody of you step inside this building? Have you ever entered it? No? It's really fantastic. I can really recommend to have a look how the situation is inside. The building itself is very, very elegant. What you see here is the southern facade, and you can see here from the inside a picture how Jean Nouvel brought in position his sun shading devices. It's a system of photo lenses that are basically controlled by the impining solar radiation. And the higher this is, the more those shading devices close. So this is basically constantly a constantly changing process, and for sure it has much influence of the quality of light at the inside as well. What can you suggest? What do you think? What could be the problem with a system like this? And consider we are located here not in Arabia, but we are located here in France, in Paris. But what do you think? What could be the problem of a sun shading device like this? Probably, yeah. But think very simply.
Glare?
Glare is probably a problem. Energy. Think of the functionality. Sorry? There are no openings, so the access to the outside is basically blocked, right? But very simple. It could break. It's very complex. And the maintenance of a system like this is a sophisticated thing. Think of the shading devices here at the Danube University. When you turn around and look outside the window, you see the new building part of the Danube University. And you see those typically vertically shading devices. And they are also changing. They are not changing by the impining radiation, but they are changing by time. There is a control system that tells the shading devices, okay, it's 12 midday, you have to be closed. And this is for us as employees and workers here at the university, believe me, it is annoying. Definitely annoying when the sun shading device shuts down and you have no longer access to the outside. You can see in a kind of scheme what is going on outside, but the access to the outside is basically blocked. And there is always some drivers that have to be maintained and repaired because the system is very sophisticated. The second thing is, and you already mentioned it, what happens if the sun shading device is closed? What has to be done at the inside? The light has to be switched on. Exactly. So we have a very high glazed building here, but on the other hand we have to switch on the lights. Because otherwise we get an overheating problem, and and this is also a kind of mismatching, so to speak, that is regardable on many high glazed buildings. So those high risers with a glazing portion of 70 or 80%. The Danube University has a glazing portion of about 80%. Those buildings are that ones that have to be artificially lighted. And for sure, but the next picture will tell us what is the source of inspiration of Jean Nouvel. For sure, it is the traditional Arabic architecture like here in a townhouse of the city of Jeddah. On the western coast of Saudi Arabia, you can see an extremely elegant and beautiful buildings with those typical building parts, the so-called ravashins. Roshans is the second word for this, where people are sitting inside those building parts in a kind of airstream, and on the other hand, this very artificial ornamentic paints of the ravashins give a certain light, but enough high amount of shading at the inside. So those shaded rooms are, so to speak, the best rooms in the townhouse here. It's very interesting to make building researches on buildings like this, because nowadays, and with so to speak, with the results of climate change, it is an interesting thing what is going on in regions where the temperatures are basically higher, and what are the interactions between those high temperatures and vernacular building response, so to speak. Yeah, so the facade and the building envelope is a major topic. And then it is for sure the designing of the interiors and of the rooms itself. So it is about proportion of rooms. It is about positioning of windows. It is about qualities of floors, walls, and ceilings. And for sure it is about orientations of the different rooms. Another example, probably one of the most interesting examples what daylighting is concerned, it's the library of the Trinity College in Cambridge, done by Christopher Wren in the 17th century, with a very, very balanced type of fenestration, with a very, very balanced type of the selections of materials for the floors, for the walls, for the ceilings. So if you get the possibility to visit this interior room, yeah, I'm sure you will be very excited. And basically we have to deal with artificial lighting as well, definitely. It is a major topic, it is very, very important for us. In 1822, when the picture of the woman at the window was painted, there was no idea of artificial lighting. The only way how those interiors could be, so to speak, artificially lighted was a flame, was nothing else than a single flame. Because the invention of the bulb was about 60 years later, 50 or 60 years later. And the development of products for artificial lighting systems yeah, are proceeding very, very rapidly, and yeah, we should be interested in this as well. And then it is about the woman at the window herself. What does she need? What is she doing inside this building? Is this a building for living, or is this a dwelling room, or is this a room for working or for healing? How old is the woman at the window? And which requirements does she have related to light and daylight? And in this case, first, Hans will give us an overview about the state of the art in this context, what is going on. And in this context, during the last, let's say, 20 years, a lot of topics and a lot of themes were discovered, especially by medicines. And the interactions between light and well-being is a topic that is really growing very fastly. And it is definitely also a topic for planners, architects, and we will try to give you an overview about those topics where we think that architects should be aware of all those things.
We have to mention it's not really new. The old Romans, the old Greek knew about it. We forgot quite a lot and became lazy because of this artificial light. I think that's an issue.
Yeah, exactly.
So I think we try to rediscover all the findings which the old Romans already had.
Yeah, right. If you try to, or if you read books of Vitruvius, one of the first, so to speak, architectural theoretics, most of those things are already mentioned. Most of his measures are also coming to the surface again, and this is really very interesting because he wrote this 2,000 years ago, but we have now the possibilities and we have now the tools to number all those things and to give relationships and to give precise information what is really going on. And in this context, the interactions between planners and medicines is very interesting.
I think you should mention your nice project.
Yeah,
it is really exciting.
In this context, we have actually a very it is a nice research project where we bring planners, medicines, psychologists, biologists, and all those scientific topics together to have a look what can we get out of this huge knowledge that is assembled in the project. What can we get out for the builders and for the planners? What should be respected, and how can it be respected, and which recommendations could we give for future buildings? Yeah. Then I think, yeah, we have prepared, so to speak, a kind of schedule for this morning. We will talk about light and radiation. We will talk about the principles of climate-sensitive design. Probably this is a kind of repetitions of topics that you already heard during the last 2 weeks. We will talk about light metrics and light quantifications. Therefore, we have also prepared some measure tools, and in the afternoon probably we will do some workshops in this context. Hans will give us an overview about light and health. What is the state of the art in this context? Hans is, in this case, always very close at the state of the art, and this is a very good opportunity to have him here, because what he will tell us is really, so to speak, the latest news, and this is a good thing. And later on, we will talk about diffuse and direct light analysis in awareness of our light lab, because we would like to show you the light lab of the Danube University in Krems, which is a very, very useful tool for the design process in case of daylight-sensitive building design. Okay. Any questions to this? Any more topics probably that you would add to your list? Otherwise, I would say let's jump into the topics. First, again, a question about the definition of radiation. What do you think? What is radiation? Radiation is the emission and transmission of energy in the form of electromagnetic waves. So this is a basic definition of radiation. The most important source of radiant power, for sure, is our sun. And the radiant power, or we can quantify the radiant power of the sun, but this number is that huge that it doesn't really make sense to explain it. But what is important for us is a second number that you probably have heard. It's the so-called solar constant. The solar constant is the average extraterrestrial intensity of solar radiation. So to speak, what is coming in from the sun to the outer surface of atmosphere. Did anybody of the lectures during the 2 weeks mention the solar constant? Have you heard about it? Yeah? Okay, this is good. Because the number of the solar constant is something with 1,367 watts per square meter. This is something that we can handle. This is something that is probably quite familiar to us. But now what is important is that the intensity of the solar radiation now is depending on the angle of incidence. The angle of incidence in this context is very, very important. Think of the position of Earth related to the Sun on the 21st of December. We see that the northern hemisphere of our Earth is aberrated from the Sun. On the other side, on the other hand, the southern hemisphere is exposed to the Sun. We have polar day on the South Pole, we have polar night on the North Pole. They completely other way around, the completely different situation is occurring on the 21st of June, where the northern hemisphere is exposed to the sun and the southern hemisphere is aberrated to the sun. And now, the solar constant and the angle of incidence, the relationship between this is going like this, yeah? For instance, if we have here, again the Earth, like the sketch here, the sun is inclining, let's say, on the equator in a vertical angle. We are, let's say, somewhere here, and the angle of incidence here, let's say, is not 90 degrees, but let's say 30 degrees. Yeah? And if we want now quantify the incoming energy, energy here, let's name this location as x, is the solar constant, E0, times the sinus of the angle of incidence. The sinus of 90, what is the sinus of 90? It's 1. What is the sinus of 30? 0.5, just a half. So with an angle of incidence, the incoming energy is just a half. And this is what we should consider, for instance, when we are talking about solar gains and things like this. We have to consider these relationships between the solar constant and the incoming angle of incidence. Also for sure depending on different facade exposures, on the north, on the west, the south, or the east. So this just as a hint that we should consider. And the knowledge about the exact position of the sun on a certain plot and on a certain season is also really of major importance. And therefore, we have the very simple and very useful tool of so-called sun path diagrams. Are you familiar with those sun path diagrams? Is everybody of us familiar with the interpretation of sun path diagrams? Okay, I have prepared some slides to explain how it works. This is here a sun path diagram of latitude 48. Vienna is approximately on latitude 48. And now let's see how it works. Think again a sun path diagram now in a three-dimensional view. If you are lying on your back with your head orientated towards the north, and you are lying here on the 21st of June, so at the beginning of summer, and you are lying there all day long, you will realize that the sun is rising left behind your head. It will take its course over the sky and it will set here in the northwest. Yeah? When you are now lying at the 21st of December, at winter beginning, the sun will rise in the southeast. It will again take its course around the sky and it will set here in the southwest. So you get two three-dimensional curves. And when you now project those three-dimensional curves, you get a sun path diagram. In this case, for latitude 58. And by the definition of two different angles about the angle alpha, the so-called azimuth angle, the aberration from the north direction, and if you take the second angle, gamma, the so-called sun height, the angle of incidence of solar radiation on a horizontal to ground level, you can define every position of the sun for every place on every season. And I have prepared for you, just to start a kind of discussion, I have prepared two sun path diagrams. One for Oslo and one for Bukit Kota Tabang. It's a city in Indonesia, just near the equator. and Oslo on latitude 59. Can you tell me, or can you explain, what are the major differences between those two diagrams? What are the major differences between the solar situation on these plots?
The angle of solar light beam
Yeah?
reaching the surface is different.
When? When is it mostly different?
When now comes the winter, the sun is coming more horizontal in the space, while in heat is going to be always more
Exactly.
on top
Yeah.
of the building.
If we, for instance, if we take the course of the sun on the 21st of December, we see that the sun height is just about 10 degrees. So the angle of incidence in winter time is just about 10 degrees. On the other side, in summertime, the difference is not that big compared, for instance, to December in the equator. If you compare this, the difference is not that high. What is also a very, very important aspect when you think about the day length here in Oslo?
The amount of daylight.
Yeah. We have a sun exposure in summer of nearly 360 degrees. On the other side, what is happening at the equator? The sun exposure is over the whole year, it's basically the same. Yeah? And this has to be respected in architecture. This has to be respected related to windows. This has to be related to sun shading devices. So this has a major influence of the designing of the building.
But there is also a difference because in Norway and in the northern part of Europe, it's like polar night and polar day when in summertime the sun doesn't move down.
Yeah.
In winter time, we have to have the same daylight lamps.
Do you come from Scandinavia?
I'm studying there now.
Ah, okay, okay. Who has ever been near the northern polar circle? How is it in midnight? Is it annoying or is it
exhausting for the
yeah?
body, for the brain, and
Yeah.
confusing.
Yeah. It's confusing. Have you been there for holidays or for working, or are you living there?
I was working there recently.
Okay, okay. I have never been there, unfortunately, but I would be very interested how it feels when you go there and when you have those all day long sun space exposure. This must be very interesting. On the other hand, sorry? And night and winters, definitely. Is it really dark? Is it completely dark, or is there?
Dark.
Yeah. So there is no kind of dusk or dawn or something like
in the
this.
cities, it's okay because there's like light pollution.
Yeah.
But if you go like more to the north, it's really
Yeah.
And for the brain, it's very confusing because your body is tired, but your brain is like it's daylight.
Go. Okay.
Yeah.
It's
your-
bright
your
outside,
brain
so.
is active. Yeah.
Okay. Okay. On the other hand, the day length as well at the equator all day long, all year long, is basically the same.
It changes a little bit in summer. It becomes more dry and hotter,
Yeah.
and there's more sun.
Yeah.
Like you feel the heat of the sun. In the rainy season, it's not so much.
Yeah. Yeah.
And it also gets to sunset later, like at
Okay.
7 o'clock.
Yeah. In this context, to mention, where is he? Marcelo? In this context, I have to mention that Marcelo did, when he did his studies here, he did a very remarkable project model for a building type. I think it was near the equator, building for a region at the equator, and the building design that he, in a very close relationships with thermal qualities of the building and the lighting qualities of the building. As good as it gets. For sure, they did not have the possibilities that we have nowadays, But the design itself is very, very smart. On the other hand, if we compare now this situation here in Austria with a situation again in Jeddah, our point cloud now here is telling us it is not about heating, definitely not. It is mostly about cooling. And if we have now a look at the design of the building itself, again, a townhouse of the city of Jeddah, we see that the house is not compact. The envelope of the building is very big. The designing of courtyard is important because the building is shading itself. And for sure, again, those building parts like the machines or like those shading devices that we have put in position on the window enables or makes it possible that the situation itself is acceptable, as good as it gets. And please consider these buildings are working without any cooling techniques or things as well. It's just the building itself that, that generates or creates those indoor comfort conditions. This is a recommendation from me to you. Have an eye on those vernacular building designs. It's quite interesting what people in former times did just with the designing of the buildings. Yeah.
So the cloud is changing and switching along the table according to the climate, but
Yeah.
the window of comfort, is it like always the same, or it's also changing according to the climate?
This is a very good question. Building physicists always are working with this window of comfort, but it is a very hard discussion. It is a very hard discussion, and it is depending on culture. It is depending on.
Because we're adapting to the climate, and for different people it feels different. Also here, while we're here, like what we're used to, and where we're not.
Well, there are. Gregor mentioned Olefanger. I think there are some critical voices now, because if you look at the way he did, some students were sitting in bikinis on plastic chairs. So I think that's not reality. And the later studies say now adaptive comfort. So you measure the difference to the outdoor temperature. And if you consider the climate here in Central Europe, you said the maximum should be 26. If we have an outdoor temperature of 37, 28 is acceptable, definitely. But what makes the big difference, and there have been a lot of studies and surveys, if people can control it by themselves. If you control it by an automatic system, people will be very, very scared about and will complain at any time. If you say, you can control the windows, do whatever you want, people are very forgiving. So I think that's the way to do it, to use to see the difference to the outdoor temperature, and if it's 8 to 10 degrees, it's fine, usually, and let people control it. Not these all sophisticated and say the user is so silly, we have to control it. No. Yeah? Give the user the chance to influence it.
Yeah, and it is also depending on our lifestyle. Actually, we are living in a kind of, or we are actually a kind of indoor society. So we very, very seldomly step outside. We most of the time spend our time indoors. If you take, for instance, those researches on the window of comfort are in a way quite old. When you take some results that come from the 19th century, and especially in France, people in this context, and in England, people in this context made some or gave some information. The window of comfort or the acceptable indoor temperatures, let's say 100 years ago, was much lower. It was about 16 or 70 degrees. 16 or 70 degrees. Also, a German study from the 30s said that the temperature must not be higher than about 22 degrees. So the lifestyle and the the culture in this context has influence on this indoor comfort. But yeah, this is a very hard discussion. We can also discuss about clothes and about what is this better word now? About
Rules or
the rules for wearing clothes at work.
yeah.
If anybody would tell me I have to wear a suit and a tie and everything, especially on summer days with an outer temperature of 35 degrees, I would not be very happy. And on the other side, it is very interesting to observe what people are doing when they are switching on their cooling systems. I was in India last year, and I stepped inside buildings where the air temperature was cooled down of 18 or 19 degrees. You come from outside, it is hot, it's 30 or 32 degrees, you step inside, wow, 13 degrees lower. This is really, and they like it, they really like it. So this is a cultural thing as well. But I think basically from our physical principles, the window of comfort of, let's say, 20 and 26 degrees is not that bad. It's for an assumption, it's not that bad. Yeah, but whenever we start with the design process, we have an eye firstly on this. What has to be done? And yeah, if you generate and illustrate and compare those HX diagrams, and you have an eye on the building principles in those regions, yeah, to discover the interaction, this is a very interesting issue. Okay, should we make a little break or should we go on? What do you suggest? Should we go on? Okay. Yeah. Okay. A little switch now. In the morning, or first, we heard that radiation is defined by the emission and transmission of energy in the form of electromagnetic waves. Okay. What you see here in this sketch is the composition of those electromagnetic waves of the solar spectrum. And basically the solar spectrum is divided into 3 parts. All of them you will know, you will see. The first part, in a wavelength of 280 nanometers, or between 280 nanometers and 380 nanometers, we are talking about the ultraviolet spectral range. It is not visible for our eye. The next range is the so-called visible range, 380 nanometers up to 780 nanometers. And this spectral range is, per definition, called as light. So when we are talking about light, we are talking about the visible spectral range, and we are talking about a very, very precise range of the overall solar spectrum, between those 380 and 780 nanometers. And last but not least, we have those near infrared light, the long wave, the longer wavelength between 700 and let's say 3000 nanometers. But this typical composition of the solar spectrum, again, is constantly changing. This is not a static curve, it is a very, very high dynamic curve. And therefore, I have prepared some slides that might illustrate this dynamic process that is going on. If you see here a picture of this mountain. Do you know this mountain? It is the Matterhorn, a very famous mountain in the Western Alps in Switzerland. And this picture was taken just before sunrise. And I would like to, have an eye on the color of the sky and on the color of the mountain and the surfaces of the forests and all those things that are visible here. As I said, this picture was done just before sunrise. This picture was taken in the moment of sunrise. We see here this reddish, yellowish reflections of the snowfields of the Matterhorn. And some hours later, again, a picture with this typical bluish sky and bright, shiny bright snowfields of the Matterhorn. If we make now with these different pictures or with this different sky situation a kind of spectrometric research on the light, we can see that the composition of the solar spectrum or the composition of the visible spectrum of the solar radiation is again constantly changing. We have here in the morning many parts in longer reddish wavelength, and on the other side we have here this typical distribution as we have it usually on middays with the highest amounts of wavelengths here in the greenish section. Another excursion later on now leads us to the artificial lighting systems, and therefore to a physical phenomenon, so-called blank body or a black body. Have you ever heard about a black body? Yeah? A black body could be basically a barbecue coal, could also be a laser pointer, could be a laptop, could be a desk. Every solid could be a black body. No liquids and no gases. This is something different. But now, if you put heat on a black body, if you put heat on the laser pointer, or if you put heat on the barbecue coal, on a certain level of temperature, a black body emits light, emits radiation also in the visible spectral range, like here. And this is probably an understandable explanation how artificial lighting systems, some of them, are working. Again, if we take this curve here, this typical distribution of the solar spectrum, this is the distribution of the emitted radiation of a black body with a temperature of about 6,000 Kelvin. Which black body, which object has a surface temperature of 6,000 Kelvin? What do you think?
Sun.
Exactly. The sun has a surface temperature of about, a little bit lower, but let's say of about 6,000 Kelvin. If we take now the radiation composition of a bulb, of a 40-watt bulb, where those wire here of the bulb has a temperature, a surface temperature of 2,680 Kelvin, we get a spectral composition like this. Yeah? So again, we have every wavelength of the visible spectrum represented here, most of them in the reddish section, but, and this is unfortunately the cause why the bulb was forbidden in the European Union, because most of the emitted energy is in the infrared spectral range. So a bulb mostly produces heat, not light. But the visual quality and the representation of every wavelength here is, from the visible point of view, spectated very, very good. Another example is those typical band spectrum of incandescent lamps, as we have them here. We see that the spectrum of those lamps show those typical peaks. So not every wavelength is represented, but just some of those peaks. And the last spectrum that has to be respected are the light-emitting diodes, the LEDs, with a typical peak here in the bluish section. And this typical peak in the bluish section is discussed very, very intensively, because it has major influence about or on our well-being and on the controlment on our hormone system. But I think in this context, Hans probably you will show us, or you will give us some more explanations to this. I have prepared not a spectrometer, but a spectroscope. And I will try to switch on the lights here so that you can see those different aspects that I showed you before regarding to the spectrum of those lights. If you take the spectrum and look, for instance, outside the window, where you see later on the spectrum of the natural light, and then if you look at the incandescent light, you see the differences between those continuous spectrums. We are talking here about a continuous spectrum and the difference to the band spectrum that you see here. I will hand over the spectroscope to you. Please give it to the colleagues. Have a look at the outside light and then the light of the incandescent lamps, and you will see the difference. This is really a very, very simple and useful tool, but it might give you good information about the quality of lighting systems. So when you are in the situation that you have to select some lamp types for your project, and you have this spectroscope with, you can get a very good impression about the quality of the light emitted by those lamps. And it's really very cheap, and it is really very useful. Okay, so this was a little excursion to the artificial lighting systems. You have again here a list of different lamp types, and as well an illustration about the spectrum that they are emitting. Again, we have here the bulb, incandescent lamps here, and this is a very important or very interesting spectrum. The spectrum of the natrium vapor lamp. It emits just in one single wavelength. So this is the lamp with a very, very high energy efficiency, but it emits just one single spectrum. You have a question?
Does the spectrum affect the way we see, like in terms of colors, or it's continuous and
Yeah, it has influence on the color renderings. It has really major influence on the color renderings. This is what I want to explain by naming this example. Because what is happening when we have, or for instance, where do you think could this type of lamps be used? What is a typical usage for this type of lamp? Would you use it in an interior room? Or would you use it in an operation room? What do you think? What could be a typical usage for this lamp? Think of street lighting. Many street lighting systems are assembled or are working with this type of lamps. But when you are talking with, let's say, with emergency doctors, and when they come to an accident, and when there is a person lying on the street, and there is some fuel, they told me that it is very hard to decide, is this fuel, is it water, is it oil, is it blood? Because you can't see clearly the color of the liquid. Because you can see you can see basically this color, this wavelength that is about on about 555 nanometers. So the energy efficiency in this case is very high, but the color renderings is very, very low. And that is why some communities and cities are changing their outdoor lighting mostly with LEDs, because the color rendering is definitely better. Yeah? So this is a small excursion to artificial lighting. Now we come to at least two photometric quantities that have to be mentioned. The first is the so-called luminous flux, or lumen. The luminous flux is nothing else than the total radiant power emitted by a light source in all directions, but without the infrared and without the ultraviolet spectral range. So when we are talking about the luminous flux, we are just talking about the visible spectral range. And what is coming in, and the portion of luminous flux that is coming in on a certain surface, the luminous flux per square meters is a number that I'm sure all of you will know. It is the illuminance, or lux. And the lux level is basically the most important number when we quantify light indoors or outdoors. I have picked out some numbers and some amounts, some typical amounts of lux. For instance, in an operation room in a hospital, there is a requirement of about 10,000 lux. In office buildings or in universities or in seminar rooms, there is a recommendation of 500 lux. In storage rooms or with lower visual requirements, we should have about 100 lux. On a bright summer's day, like this morning or this midday, we can assume that there is a lux level outside of 100,000 lux. So you see that the gap between inside and outside what the lux level is concerned is very, very high. And you can also see the ability of our eye to adapt on those circumstances. So our eye in this context is very, very patient, let's say. But more of this a little bit later on as well. Now we come to, with this knowledge about those photometric, or with this light metrics, we come to the topic of light quantification in interiors. And you will probably be wondered why there is the illustration of a constantly overclouded sky. A constantly overclouded sky is a circumstance when light levels in interiors have to be quantified. It is because, and this leads us now as well to our light lab, probably it makes sense to first to explain the systematics of our light lab. The light lab itself is nothing else than a half dome with a diameter of about 6 meters. And on this half dome construction, 230 halogen bulbs are mounted, 230. And these bulbs are driven in a way that the light intensity on the zenith is three times higher than down here on the horizon. So we are talking about a 3-to-1 sky. And this is the characteristic of a constantly overclouded sky. Remember, or imagine you have a rainy day and you have a look at the distribution of light in the sky. You will recognize that the brightness on the zenith is 3 times higher, or is about three times higher than down on the horizon. And this characteristic is equal for cramps, for the North Pole, for equator, for every plot on Earth. A constantly overclouded sky has this typical characteristic of a brightness distribution of 3 to 1 between the zenith and on the horizon. And then we can quantify by measuring the lux level.
Maybe to add, in this respect, it doesn't make any difference if it's oriented north or south or west or east. It doesn't matter, because the sky is totally equal.
Genau.
Yeah.
And this makes things comparable.
Yeah.
We already heard that the direct light impact is constantly changing. It's depending on the latitude, it's depending on the season, it's depending on many other things. But a constantly overclouded sky with its characteristics is always the same. And with this comparable circumstances, we can now calculate a certain unit, the so-called daylight factor. And the daylight factor is nothing else than a ratio between the illuminance level, the lux level, inside and outside. So we take our measure tools, I have prepared some here, and we will use them in the afternoon, and we are able, in a very, very simple way, to measure the lux level outside and inside. And by using these forms, the interior level, the exterior level of lux, we can quantify the daylight factor. And if somebody asks you, how much light do you have inside your building? How much daylight do you have inside your building? You can answer this question by naming the daylight factor. And there is a recommendation for daylight factors in interiors. It should be actually 2%. But in this context, we get more information from hand.
Yeah.
In 2009, the recommendations recommended a daylight factor of 1%. So 1% of the outside illuminance should occur at the inside. 1 single percent of the outside illuminance should occur at the inside. This sounds quite as a very, very low level. We think that it is a very, very low level, and it is up to us to make design decisions to raise that number, but regarding the energy impact and the overheating potential of the building.
I think it was your recommendation to say, do not overdo it. The maximum should be not more than 10% in respect of Austria.
Yeah. And how can we now calculate, or how has this daylight factor be calculated? If you do it according to the norm, if you do it without any computer simulation software, just by measuring, the daylight factor should not be measured near the window. It should, on the other hand, not be measured in the back of the room. It should not be measured on the ceiling and not on the floor. It should be in the half depth of the room, yeah, and on a level of about 85 centimeters above the floor. So let's say on the height of a working table, for instance. And if you take 2 measurings, you take the average factor of the 2 measurings and you get the daylight factor. What we did in this context was, and this happened in a very, very good and close relationship with Velux, we built a model of a certain building. So there was a very, very interesting design process in the forefield, and we got later on the building itself. We built a model out of this. We took our measure tools and we measured step by step with a very, very tight grid of measure points